Dependence of rate of reaction. Let us perform an experiment for the reaction A plus B to give C. We have reactant A in one test tube and reactant B in another test tube. Let us react them and thus C is formed. Let rate at which C is formed is equals to X units. Now let us increase the concentration of reactant B. Now we react A and B and thus C is formed at T is equals to T2. Let rate at which C is formed is equals to Y units. From this, we conclude that on changing the concentration of reactants, the rate of reaction changes. Let us now perform the same reaction at an elevated temperature. Now let us subsequently heat the mixture. Let rate at which C is formed is equals to Z units. We now find that Z is greater than X and Z is greater than Y, where X and Y are rate at room temperature. Temperature dependence of the rate of a reaction. Most of the chemical reactions are accelerated by increase in temperature. It has been found that for a chemical reaction with rise in temperature by 10 degree, the rate constant is nearly doubled. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation K equals to A e की power minus EA upon RT, where A is the Arrhenius factor or the frequency factor. It is also called the pre-exponential factor. It is a constant specific to a particular reaction. R is a gas constant and EA is activation energy measured in joule per mole. It can be understood clearly using the following simple reaction. H2 plus I2 gives 2HI. According to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. It exists for a very short time and then breaks up to form two molecules of hydrogen iodide. The energy required to form this intermediate, called activated complex, is known as activation energy. It is obtained by plotting potential energy versus reaction coordinate. Reaction coordinate represents the profile of energy change when reactants change into products. Some energy is released when the complex decomposes to form products. So, the final heat of the reaction depends upon the nature of reactants and products. The distribution of kinetic energy may be described by plotting the fraction of molecules, that is Ne by Nt, with the given kinetic energy, that is E, versus kinetic energy. Here, Ne is the number of molecules with energy E and Nt is the total number of molecules. The peak of the curve corresponds to the most probable kinetic energy, that is kinetic energy of maximum fraction of molecules. There are decreasing number of molecules with energies higher or lower than this value. When the temperature is raised, the maximum of the curve moves to the higher energy value and the curve broadens out. that is, spreads to the right such that there is a greater proportion of molecules with much higher energies. The area under the curve must be constant since total probability must be 1 at all times. Increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than Ea. It is clear from the diagram that in the curve at T plus 10, the area showing the fraction of molecules having energy equal to or greater than activation energy gets doubled, leading to doubling the rate of a reaction. In the Arrhenius equation, the factor e to the power minus Ea upon RT corresponds to the fraction of molecules that have kinetic energy greater than Ea. Thus, it has been found from Arrhenius equation that increasing the temperature or decreasing the activation energy will result in an increase in the rate of the reaction and an exponential increase in the rate constant. Now slope is equals to minus Ea upon R and intercept equals to ln A. So we can calculate Ea and A using these values. We know that at temperature T1, ln K1 is equals to minus Ea upon RT1 plus ln A, and at temperature T2, ln KT is equals to minus Ea upon RT2 plus ln A. Note that A is constant for a given reaction, and K1 and K2 are the values of rate constant at temperatures T1 and T2 respectively. Now subtracting the above two equations, we get ln K2 minus ln K1 equals to Ea upon RT1 minus Ea upon RT2. On simplifying, we get ln K2 upon K1 equals to Ea upon R of 1 upon T1 minus 1 upon T2. Now, log of K2 upon K1 equals to Ea upon 2.303 R of 1 upon T1 minus 1 upon T2. On further simplifying, we finally get log K2 upon K1 equals to Ea upon 2.303 R of T2 minus T1 upon T1 T2. Let us now understand rate of a reaction also depends on catalyst. Substances which alter the rate of a chemical reaction and themselves remains chemically and quantitatively unchanged after the reaction are known as catalyst. Let us take the example of decomposition of potassium chlorate without adding of any foreign compound. Take potassium chlorate, that is KClO3, in a flask. Now subsequently heat the mixture. Observe that the formation of products, that is KCl and O2, is at a slow rate and at a high temperature of 653 Kelvin. Now we add a foreign compound, that is manganese dioxide, to potassium chlorate and perform the decomposition. Now we heat the mixture very strongly. We observe that the formation of products is at a faster rate and at a lower temperature of 473 Kelvin. Here the foreign substance, that is MnO2, act as a catalyst and it accelerates the reaction, and also note that its composition remains unchanged throughout the reaction. Effect of catalyst. A catalyst is a substance which alters the rate of a reaction without itself undergoing any permanent chemical change. For example, MnO2 catalyzes the following reaction so as to increase its rate considerably. That is, for the reaction, KClO3 on decomposition gives KCl plus 3 by 2 O2. The action of the catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and the catalyst. It is believed that the catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between reactants and products, and hence lowering the potential energy barrier. A catalyst does not alter Gibbs energy, that is delta G of a reaction. It catalyzes the spontaneous reactions but does not catalyze non-spontaneous reactions. It is also found that a catalyst does not change the equilibrium constant of a reaction. Rather, it helps in attaining the equilibrium faster. Collision theory of chemical reactions. It is based on kinetic theory of gases. According to this theory, the reactant molecules are assumed to be Hart's pairs, and reaction is postulated to occur when molecules collide with each other. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency, that is Z. Another factor which affects the rate of chemical reaction is activation energy, as we have already discussed. For a bimolecular elementary reaction, A plus B gives products. The rate constant for this reaction is given by ZAB multiplied by e की power minus EA upon RT, where ZAB represents the collision frequency of reactants A and B, and e की power minus EA upon RT represents the fraction of molecules with energies equal to or greater than EA. The above stated equation predicts the value of rate constant fairly accurate for the reactions that involve atomic species or simple molecules, but for complex molecules, significant deviations are observed. The reason could be that all collisions do not lead to the formation of products. The collisions in which molecules collide with sufficient kinetic energy, that is, threshold energy and proper orientation, so as to facilitate breaking of bonds between reacting species and formation of new bonds to form product, are called as effective collisions. For example, formation of methanol from bromoethane depends upon the orientation of reactant molecules. The proper orientation of reactant molecules lead to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. To account for effective collisions, another factor P, called the probability or steric factor, is introduced. It takes into account the fact that in a collision, molecules must be properly oriented. That is, rate constant is equals to P ZAB e की power minus EA upon RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision, and hence the rate of a chemical reaction. Collision theory also has certain drawbacks, as it considers atoms or molecules to be Hart's pairs and ignore their structural aspect. Let us now understand rate law. We know that rate depends on concentration of reactants, temperature, and catalyst. Let us fix temperature and catalyst for a particular reaction. Then, rate law is representation of rate of reaction in terms of concentration of reactants. Let us understand rate expression. Consider a reaction AA plus BB gives CC plus DD, where A, B, C, and D are stoichiometric coefficients. The rate expression for this reaction can be written as rate of a reaction is directly proportional to concentration of A to the power x multiplied by concentration of B to the power y. Here, x and y can be any number, that is, fractions, integer, or 0. So, rate of a reaction is given by k times concentration of A to the power x multiplied by concentration of B to the power y, or rate of decrease of reactants is equals to rate of increment of products, which is equals to k times concentration of A to the power x multiplied by concentration of B to the power y. Definition: the equation which relates rate of a reaction to concentration of reactants is called rate law or rate expression. Now, we will understand how to determine x and y in a rate law. Consider a reaction AA plus BB gives CC plus TD. The rate expression is given by k times concentration of A to the power x multiplied by concentration of B to the power y. Here, x and y have to be determined. Now, moving on to the solution. Imagine an experiment with A and B as reactant. Its rate law is given by k times concentration of A to the power x multiplied by concentration of B to the power y, and let it be equation number 1. Keeping concentration of B constant and doubling the concentration of A, the rate of new equation is given by k times concentration of 2A to the power x multiplied by concentration of B to the power y, and let it be equation number 2. On dividing equation number 1 and 2, we get rate of old equation divided by rate of new equation equals to k times concentration of A to the power x multiplied by concentration of B to the power y divided by concentration of 2A to the power x multiplied by concentration of B to the power y, which is equals to 1 upon 2 to the power x. Now, taking logarithm on both the sides, we get x is equals to minus of log of rate of old equation minus log of rate of new equation divided by log 2. Similarly, we can compute y by keeping concentration of A constant and doubling concentration of B. Note that while performing the experiment, the temperature and catalyst should be constant.